Okay. Okay. So, so you can see that increasing complexity, okay, is going to increase the accuracy. Okay. Of course, I mean, that's this accuracy is calculated based on the training data set. Okay, it's based on training data set only. Okay, so so we know that, okay, this is like a, there's a trade-off between the complexity and the accuracy. Okay, so the polynomial of order 5 able to capture the data without missing a single data point, because we have only 6 data points in this particular example. So obviously, the model of order 5 has 6 unknowns, which is enough for us to capture these 6 data points without any problem. Okay, I mean, we learned that from the high school math. Okay, so but this really, okay, just memorizing stuff. Okay, because, okay, when you create a model, what you want to capture from the data set is the trend, not just memorizing the data, okay, in the data set. Okay, no. What we want to explore is the trend in the data set. So, for example, okay, you see this 6 point, 1, 2, 3, 4, 5, 6. You can see that, most likely the future data will appear somewhere along this line. Okay, I mean, this is the trend. Okay, this is shown in the trend. Okay, I mean, as a trend. So, but obviously, if you use this model of order 5, you can obviously see that, okay, after this point, this model will jump very high, right? And after this, before this point, this model is going to go down very deep as well. So most likely, this model of order 5 does not capture the trend of this data point. Although, okay, if you evaluate the accuracy of a model by the training data set, yeah, this model gives you the most accurate one. Okay, but this is normally not what we really want. Okay, so imagine if we get more money or time and we are able to collect more data points. Say we are able to collect 2 additional points, 10, 9, 7, 7. So these 10, 9, 7, 7 are represented by these 2 squares here. Okay, which, by the way, fits our intuition, right? Because these 2 points appear close to this direction, right? So it is reasonable additional data point to add. But if you look at the arrow of these 2 data points, you will find that, okay, the arrow, okay, from the linear model is much smaller than the arrow. For the model is order 5, right? So this is like the model, okay, the order 5 model does a very poor job at generalizing to future unobserved but potentially observable data. Okay, or put it another way, okay, when you use this model for prediction, okay, because when you do the prediction, you are supposed to use like something that will happen in the future, okay, to fit to your data, your model, right? So obviously that future data will not appear in your training data. So no matter how accurate your training data show you, okay, the accuracy of the training data does not, is not an indication of accuracy for the future data. So for the future data or for the test data, okay, I mean, if you allow me to use like machine learning jargon, okay, then the accuracy and the complexity of model will look like this, actually. So, okay, so overfitting is a general problem where model fits very well with the data set that was used to learn its parameters in the first place. So this is the training data, okay? So, but it's very bad at fitting other data set. We say that we have overfitting. This phenomenon, okay, that the model perform well in the training data set. I mean, when I say perform well, I mean the error is small in the training data, but is large in the test data or in the future unobserved data. We call such a phenomenon as overfitting. So this is a very general problem in statistics and machine learning. So a very useful way to picture the problem of overfitting is by thinking that data sets have two components. There are two components in the data set, the signal and the noise. Okay, the signal, okay, aka the trend, okay, I previously used the term trend. That actually just represents the signal. Okay, this part, the signal is, or the trend is what we want to capture by the model. Okay, so the future data or test data, whatever we call that, okay, will obviously, follow this signal or follow the trend. Okay, so it is very important that your model capture this signal, okay, or the trend. Okay, but the noise is what you have, okay, when you are doing data collection or when there's more function for the sensors or the limitation of the measurement tool. Okay, a lot of this will contribute to those errors. Okay, so those errors, okay, the errors are the one that we want to ignore. Okay, we want to ignore from the data set, but because the data set contain these two components together, it's very difficult for you to tell which part is the signal, which part is the noise. Okay? So a model overfits when it is so flexible that it learns not only the signal but also the noise. Okay? So it learns the noise too well and it will hide the signal. Even though normally it also learn the signal, but because the noise, okay, it actually hide the signal. Okay, this is a practical justification for Occam's razor. Okay, that's why we prefer simpler model. Okay, remember Occam's razor suggests us to take a simple model, right? So this is a justification for that. Okay. So in principle, we can always create a model so complex that it explains everything in detail. Okay, if you have a model, okay, if you have a data set like 100 with 100 data points, we can have a model with like 99, auto 99, so that we can capture everything, right? Every detail. Okay, as for example, just like in the empire, okay. This is like a example that actually I think this is a story up here. Like I forgot it's in the like coming in a children's book or something. But it's like in an empire, an emperor asked like you know the cartographer, you know cartographer, the guy who make maps. Okay, the guys who make maps. The emperor asked the cartographer to create a map for his empire. Okay, and the emperor asked the cartographer to create that map to be as detailed as possible so that it captures everything in his empire. So it turns out that map is of size of his empire. It's huge. Okay, it's so big, like it's as big as his empire. So let me ask you this. If you have such a map, is it going to be helpful? No, it's too big, right? Nobody use that such a big map for direction, right? If you have a map this big, you use that for correct direction, that's reasonable. But if you have a map that's like you know, as big as this house, can you use that for direction? No, right? You just it's impossible for you to navigate by that map. It's too big. Not mention like the map is as big as the whole country. That's useless, right? That's useless. Okay. So same thing here. Okay. You don't want a model so complicated that it captures everything. Okay, because you don't want to recreate the noise. The noise is not what you want. Okay? But on the other hand, remember this part. Okay? If the parameters in your model is too few, okay, the model may not be complex enough to capture the signal. Okay, if that happens, we call that your model is underfitting. Okay, that's opposite of overfitting. But basically, okay, for example, let me use this example. Okay, we see the model of order 0 represent the average of those data points, right? Well, but it really doesn't give you much detail, right? Only the average, but nothing more. And the R² value is crazy. I mean, it's 0. Okay, so it's not that useful, right? It's really not that useful. So this order 0 model, obviously we have underfitting here. Okay, we have underfitting. So we don't want overfitting, obviously. We don't want underfitting either. So that's what I meant by it's important to find that sweet spot. You want a good level of complexity, not too much, not too small, just right level of complexity. Okay, so that's why this question is difficult, and that's why we need model comparison, because we may need to create several models of different complexity and see which model is better. Okay? So another way to describe this trade-off between the complexity and accuracy is called variance and bias. Okay, the variance is like the bias is the result of model with low ability to accommodate the data. So if your data has a low complexity, for example, like the model with order 0, okay, it really doesn't have enough like ability to accommodate our data set. So that's called high bias. Okay, so high bias can cause a model to miss relevant pattern and lead to underfitting. So another factor is called variance. High variance is a result of a model that has high sensitivity to details in the data. So the model is very flexible. But when you have a high variance, the model may be too much accommodating so that it can not only learn the signal but also the noise, which as a result will lead to overfitting. Okay, so this is another way to say the trade-off between the complexity and the accuracy. I mean, we can rephrase this as the trade-off between variance and the bias, but they pretty much means the same thing. Okay, so we want, this quote is from Einstein. Okay, things should be as simple as possible, but not simpler. This is a sentence. The sentence from, said by Einstein. I mean, he's obviously a famous guy, right? And you can see that this sentence captures, okay, exactly the meaning of like what we are talking about. We don't want underfitting. We don't want overfitting. We want something in between. Okay, that's exactly what the meaning of this word. So in the slide 25, the order 0 model is the one with the higher bias, okay, because it's biased to return a flat line, okay. So yeah, I think I already mentioned that, okay. So okay, so a model with high bias, model with more prejudice, okay. This is just like you are trying to use anthropomorphization, okay, 拟人化，just kind of like treat the model as a person, okay, because prejudice is like used for some people, okay. If you have prejudice, this means like you have like your opinion is not correct, something like that. Or more inertia. Inertia is like from physics, okay, from physics. So inertia means like 惯性. Okay, 惯性. If you know a little bit about physics, I mean, you guys have taken like physics from high school, so you know what inertia is, right? So with a high bias, it's like prejudice or more prejudice or more inertia. Okay, so while a model with high variance is a more open-minded model. So model is, again, this is like we try to treat a model as a human. Okay, so we say it's open-minded, but you get an idea. Okay, so it's more so. If it's too biased, then you are ill-equipped, to accommodate new evidence. But if a problem, if the model is too open-minded, then you end up believing like a nonsensical stuff. Okay, so just like a person. Okay, a person cannot be too prejudiced or it cannot be too open-minded. I mean, you have to be, somewhere in the middle. Okay. So that's like, again, this is just to describe the bias variance trade-off, okay? So in the previous example, it's more or less easy to see that the order 0 model is very simple. Order 5 model is too complex, Okay, but what about the other two? The other two, what are the other two? The linear model and the quadratic model, right? Okay, so to answer this question, we need more principled way of taking into account the accuracy on the one side and the simplicity on the other. Okay, so that's where the model comparison come into play. To do so, we will need to introduce several new concepts. Okay, the first two are within sample accuracy and out of sample accuracy. The within sample accuracy is the accuracy you measured from the training data. Okay, and out of sample accuracy is the accuracy you measured from the data that is not used in the training, for the training. We can say it's test data, something like that. So obviously, okay, the out of sample data, accuracy is a lot more important than within sample accuracy. Okay, we want the data to, we want the model to perform better for the samples that are not in the training data. We already know the training data set, right? So if you just use the training data, again, you don't need a model. You just the result is already there, right? So you really don't need a model to answer any question that comes from the training data. What you need is, what you need a model to answer is the out of sample question, the sample that comes from outside of the training data. That you need the model to answer that. So that's normally what we want the model at the first place. So this out of sample accuracy is actually more important. Okay. So however, generally, there is a problem with this. We need to be able to afford leaving aside a portion of the data, not to feed the model, but to test it. So that's where we normally want to divide the data into multiple portions. Okay, part of it to use for the training data. The other part we want to leave it for to test the accuracy. Okay, we want to leave it as out of sample data to measure the accuracy of the model. Okay, but this is very expensive. Okay, because I want you to be aware. Okay, in deep learning or in other machine learning paradigm. Okay, it's common, it's natural to divide the data into maybe training data, validation data, and the test data. This is very common, very common. But this is not that common for Bayesian data analysis to do that. Why? Because the data, the size of the data that you use for Bayesian data analysis is normally a lot smaller than the size of data you use for deep learning or like a machine learning. Let me put it this way, okay? If you use a data set for Bayesian data analysis, normally the size of data is within tens or hundreds. Okay, and if you want to use machine learning to do the problem, the size of the data set is normally thousands. Okay, thousands. Okay, to maybe tens of thousands. Okay, but for deep learning, you definitely need the data set to be higher than tens of thousands. So the problem that you apply, the approach, okay, is different. Okay, different problem require different approach. okay, I mean, the size of the data set is an important key, okay, to identify like a right model to use, okay. If the size is small, well, you don't want to use machine learning. You don't want to use deep learning, okay, because obviously it doesn't work, okay. But yeah, but at the same time, because I mean, for Bayesian data analysis, because most of the time, I mean, the size of the data is so small, it's not affordable to divide the data further. Okay, we say, well, we break. I mean, we just like leave like maybe 20-30% data for test purpose. Well, in the other area, okay, for the other approach, that's probably possible because of the size of the data set. But for Bayesian data analysis, this is going to be a problem. Okay, this is going to be a problem. So to fight with that, how do we fight with that? I mean, we want to use all the data to train the model, as much as possible, at least. Okay, so how do we do that? There are two methods. Okay, one is called cross validation. The other one is information criteria. Okay, the cross validation, you divide the data set, the whole data set, into k subsets, and then you do the things like you try to train like multiple models, actually k models to be exact, and then you use these k models, the average of this k model, I mean, to see the accuracy. So that's like how the cross validation works. I will explain in more detail, okay, shortly. And the other is called information criteria. This is like you don't break it into like a training set and test set. Okay, you just use the whole data set to do the training. But after that, okay, you will try to discount. You'll try to discount the accuracy, or you discount the in-sample accuracy to approximate the out-of-sample accuracy. Okay, so we are going to talk about these two things. Yeah, I hope to cover cross-validation and at least part of information criteria in the final, but that's about it. I mean, I don't think we can finish everything anyway. Okay, and also as I say, like a lot of this is they are very dry. So I don't want to bore you guys to death. Okay, for those dry material anyway. Okay, so what is cross validation? The cross validation is probably the best to be introduced by this figure. So say this is the data set. Okay, and here we try to break it into k portions. Okay, and each portion is roughly the same size. Roughly the same size with similar property. Okay, for example, if you have like different categories, different classes, you want to leave like each class to be about the same distribution as in each portion. Okay, each portion. I mean, for example, like say the whole data set, you have two classes. And the first class is has a ratio of 2. The second class has a ratio of 1. Okay, the first class, the second class, the ratio is 2 to 1. Then for each of these k subset, you also want to maintain that ratio, 2 to 1, 2 to 1, and you just draw the sample randomly from like different classes. Okay, so anyway, so you form this k subset. So the first round, you use the first subset as a test data set, and use the remaining data set as the training data set, and you get a model A1, right? And the second round, okay, you use the second subset as a test data set, and the remaining data set, the blue one, as the training data set. You get the result, as A2. This result, okay, this result represent the accuracy of this test data set. Okay, this A1 is the model you obtain from this training data set, and then you use this test data set to see the accuracy. That's A1, and so on. And the third round, you use the third subset, okay, as a test data set, and the remaining data set as a training. Okay, so you can do this for obviously k rounds, right? And then your accuracy, okay, will be approximated by the average of this k, AKs. Okay. So this is called the k-fold cross validation, where this k represents how many subset you divide the data. Okay? If you divide the data into 10 subset, then you need 10 rounds. That's called 10-fold cross validation. Okay? So obviously, cross validation results in more computations, right? If you don't divide the data into so many subsets to do the k-fold cross validation, you only need to compute one model, and you only need to compute one accuracy, right? But now you need to do these k rounds, and in order to approximate the out of sample accuracy. Okay, so this the cross validation is a very simple and useful idea. Not only we use that in the Bayesian data analysis, actually this technique has been applied to machine learning in general very, very often. Okay, so keep that in mind. Okay, this is like a very well-known approach in machine learning field. Okay, and also, okay, some people, okay, feels like there's one more thing. Yeah, there's one more thing. Obviously, okay, if you go extreme, okay, say you have like 100 data points, okay, if you go to the extreme of this approach, you could, for each data set, you have only 1 point. You have only one entry. Okay, and you use rest of the data set for training, and use that one particular data set for testing. Okay, and obviously, okay, if that's the case, then the k becomes like as large as like the size of data set, right? Okay, but okay, we normally call that approach, okay, as leave one out cross validation, LOOCV. Okay, but obviously, okay, if you use like this approach, you need to train so many models, right? You need to train so many models. I mean, as as many as like the size of the data, training data. But so sometimes when doing LOOCV, the number of runs can be less than the total number of data points if we have a prohibited number of them. So if the data set is too large, okay, we probably only want to try to do it like say like if the data set is 100, we don't want to do like this thing 100 times. We probably do it like maybe 30 times or something like that. I mean, remember, we get all these. The purpose, what is the purpose? What is the K4 conservation? The purpose of K4 conservation. The purpose of K4 conservation is to approximate our central axis. Okay? So if you already collect like maybe 30 rocks from the LOOCV, okay, that average may already be accurate enough for the our central axis anyway. Okay? I mean, you, of course, more rocks, okay, generally, it's just like you have more central. I mean, you get a better idea of the whole data set. But you know, there's a trade-off between the computation cost and the accuracy. Okay, so I just want to say that the LOOCV, in LOOCV, the graph may be smaller than the size of the data. Okay, the number of may be smaller than the size. Okay. That's all the course equation. Okay. And the next topic is information criteria. Okay. The information criteria, okay, actually, as I said, is like it gets like accuracy from the three sample accuracy, but it is trying to do a discount from that. And that discount is actually derived from information field. So mathematically, it's very complicated. So the only problem you can do is like some of them. Just tell you probably how to use that. So we are not going to go into details of how those are. So, and to be more specific, okay, what I'm going to do is that I'm going to just talk about one. Okay, there are so many. Okay, for example, here, there's law that this one has this is not anyway. So if you want to measure how well now fit the data to complete. Okay. So this one, okay, is programming between the data and the prediction. The programming error. I think everybody knows that, right? Okay. This is not one of the measures for the MSC, right? Mean square error. So if you have done a little bit of data science, you know mean square error. And that is thank you. Okay. So the strategy of why I think is specific that even the estimate. So this is the true mean square. And so the square error will show that equal if you do not cancel out each other. So why do you need to do this square? It's just because of you want the error. For example, if this is the error, positive, the other one is negative. You don't want to simply add up
these two values because they will cancel out each other, right? So we use square so that everything tends to be positive, right? That's perfect. The arrows do not cancel out each other. Okay. The second thing is that we want the arrows to be as small as possible. So we want to penalize the bigger arrows. We do a square, like obviously, like bigger arrows will get much higher value, right? So because of these two reasons, the mean square error is first. So mean square is first. So another way, okay, there are other ways to compute similar problems. For example, you can use the absolute value. Okay. If you use absolute value, obviously errors will not cancel out each other, right? But you will not be able to penalize larger errors over small ones. Okay, that's right? And the more general measure, okay, is to compute the log likelihood, which is the log likelihood. So when the likelihood is normal, okay, it turns out to be proportional to the projected for the historical reason, we don't use this term, okay, for model measures. Instead, okay, we define this one as an easier. Okay, so it's negative 2 times this okay, so because we have a negative 2 attached to it, previously, okay, this one follows the same error, right? So the smaller better. Okay, the smaller better. But now, because we have negative 2 attached to that, we multiply this by negative 2. So the larger the better. Okay. The bigger is they are Asian and non-Asian. The difference goes up. So the lower it is, the higher the likelihood. Okay. And the higher the the lower the figure, the higher, actually, the higher likelihood, not likelihood, the lower the figure, and the higher the agreement of the model prediction and the data. So it's better. So we want the lower figure. We want the lower figure. The figure measures the reaching sample accuracy model, and the complex model will generally have a lower figure than simple. Because after all, we remember here I talked about so this category from here, all these tools are computing the sample accuracy, right? Okay, so we first calculate that, and then we try to apply categorization first. So pretty much all these information criteria have something to do with the form of this video. Okay, so this is one of them. Okay, called a type information criteria. Really, AIP. But okay, so this form is very close to the initial video. So as I said, there are so many of them. I will not go into the details. And also, okay, the important thing is remember I said we will have a penalization term, right? To adjust. Because this portion measure the in-sample accuracy, right? And I said the in-sample accuracy is normally too high, right? It's normally too high, so which is not, it doesn't represent all of them. Okay, we want measure all of them. Okay, so because this first term normally represents in-sample accuracy, so we have second term. This second term is 2 times PAID. This P, okay, is like the size, the number of parameters. Okay, the number of parameters. So, here. The second term penalized compact model. The more complex the model, the larger this term. Okay, so the resulting AIC is going to be larger. Okay, the larger the AIC, okay, the higher this is sort of representing the median, right? So we want the lower median, right? The lower median represents better model, right? So this penalized term will increase the median. Okay, so that's the criteria. That's the information criteria. I'll take the information criteria. I just use this as an example to show you the general form of information criteria. Okay, it's always a term, something like this that represents median. And another term is the penalization term, okay, which is relevant to the size of the model, complexity of the model, or the number of parameters of the model. Okay, and the larger the model, the higher the parameter. So that's something I want to do. So I will not go into the details. It's not the main concept about that. So, okay, let's take 10 minutes break. We'll come back. We'll talk about this. Which is